In this video, we are going to derive formula for torque on a current loop in magnetic field. Already you know that current carrying conductor in magnetic field, it produces Lorentz force, and the formula for Lorentz force F is equal to IL cross B, right? You have even derived this formula and you are familiar with this, right? Now first we will to derive torque on current loop in magnetic field. First we will discuss about the diagram, right? You can see PQRS is a rectangular coil. Okay, I is the current in the coil. You can see the current flows through the coil. Now PQRS, I can call it as a current loop, right? Now N, you can see the north pole of a magnet, and the other side you have the south pole of the magnet. That is, the magnetic field acts from north pole to south pole. That is the area of the loop, I mean the current loop, the entire current loop is subjected to magnetic field. Now the area of the loop, I mean the rectangular loop PQRS, I will divide it into 4 segments, children, for convenience sake. PQ as the first arm, QR as the second arm, RS as the third arm, and SP as the fourth arm. First, second and third 4 arms are there in this PQRS rectangular coil. And in each and every arm, I have considered the magnetic field. Okay, for convenience sake, and each and every arm, I have considered the magnetic field B. Right? Now, we will see what is this N cap. You know that the area of this loop, rectangular loop, area of the loop, let it be A. Children, you can consider this PQRS as a rectangular loop. This is the rectangular loop, and this part, what you call it as area of the loop, right? This is the area of the loop, and you know that area is a scalar. If you want to convert it into a vector, you have to consider a normal, and you can see this is the normal, children. This is the normal to the loop, right? This is the N cap, otherwise I will say it as the N cap. This is N cap, normal to this area, and so this normal you can also say it as A vector, right? The same thing I have marked here, N cap, okay, unit vector at an angle theta with respect to B, okay, that is the magnetic field. Note it down, children. And the next thing you have to note down is this length of the coil PQ and RS. These either length, okay, the length PQ and RS both are of length A, okay, and QR and SP both are of breadth of the coil, let it be B, okay, A, length of the coil, and this is the breadth of the coil, right, children? Now you can see I have drawn normal to this arm, QR arm. I have drawn the normal to this length QR. I have drawn a normal, you can see, and this normal is at an angle theta with respect to magnetic field, right? Next, same way here also you can see to the arm SP I have drawn a normal, and this normal is at an angle theta with respect to B. Okay, children. And in each arm I have marked I, right? That also you have to note down. Okay. Children, N cap is the unit vector normal to the plane of the loop at an angle theta with respect to B. Now what you are going to do is, for each arm we are going to calculate force, right? Using Lorentz force, you are going to calculate force on each arm, okay, force on arm PQ, force on arm QR, force on arm RS, and force on arm SP. First we will calculate the force on this arm, okay, which arm? PQ arm, okay. First you will force general formula, you know, F vector is equal to IL cross B, right? This is the general formula. On this arm FPQ, length L, you know, we are representing it by A cross B, okay, cross B vector. Now you can what is theta, children? Theta, IL cross B, IA cross B, that is IAB sin theta, right? Now instead of sine theta, theta I have used for some other purpose. Theta is the angle between n cap and b. So instead of angle, I am going to represent angle between this I and b. IA vector and b vector, I am going to consider it as alpha, children, not theta. So alpha is the angle between these two, right? So if you see alpha, it is the angle between I vector and b vector. You can see IA vector and b vector. This is the angle. You can see it is 90 degree. So sine 90 is 1. You can write FPQ is equal to IAB, right? If you apply Fleming left hand rule, children, you can see that the force will be acting upward. While applying Fleming left hand rule, you know that the forefinger represent magnetic field, middle finger represent the current, and the thumb represent the force, right? Force on the conductor. If you apply at this point, you are going to apply left hand rule. You can see that B, forefinger is along the direction of B, and the current is downward, right, children? So if you keep the middle finger downward, which represent current, you can see that the thumb, it will be coming out of the paper. Okay, it will be coming towards you. That is the force on this arm, it will be vertically upward, right? What I mean is, if this is the PQ arm, this is PQ arm, the force is, it will be acting vertically upward. PQ arm, it raises up, it starts to move this way, right? It starts to move upward. Got it, children? Next we will calculate force on the arm QR. This is QR arm, right? So force on the arm QR is FQR vector is equal to IB. You know this QR length is B cross B vector, right? So the angle between I vector and B vector, you can see I have written it as alpha. Alpha is the angle between IB vector and IB vector and B vector, capital B vector. I have, see, I vector I have drawn in green color, and B vector I have drawn in orange color. Okay, so the angle between this B vector and I vector is alpha. You want to find alpha. To what is this alpha, children? You can see that this is 90 degree, right? This is 90 degree and this is theta. From 90 degree, if you subtract this theta, you will get alpha. So what is alpha? Alpha is equal to 90 minus theta. Okay, if you substitute 90 minus theta, sine 90 minus theta, that is nothing but cos theta. So FQR is equal to IBB cos theta, and the direction of force, it is acting downward. Okay, you can refer this diagram, it is acting downward. Okay, children. Next, we are going to calculate force on the arm RS, children. You know that this is arm RS, right? This is the arm RS. So, FRS is equal to I. Instead of length, you are writing A cross B. And you can see the angle between I vector and B vector is alpha. You can see alpha is 90 degree. Angle between I vector and B vector 90 degree. So, if you substitute sine 90, you will get 1. So, force on this RM is equal to IAB. You can see the force by Fleming's left hand rule. You can say that this force on this arm, RS arm, it is acting downward. Okay, FRS, force on the arm RS, it is acting downward. Okay, children. Now we will calculate force on the other arm. Leftover arm is SP, right? So we will calculate force on this arm SP. FSP is equal to IB cross B vector. So now IBB sine alpha, right, children? IBB sine alpha. What is alpha? Alpha is the angle between these two. If you look here, angle between this I vector and angle between IBB and alpha is the angle between these two, I vector and B vector. You can see it is 90 plus theta. Okay, so if you substitute 90 sine 90 plus theta, that is nothing but cos theta. So FSP is equal to IBB cos theta, and the direction of FSP is upward, right, children? You can note down, it is upward. Here you can see the force on this arm is downward, whereas in this arm it is upward. Okay, here children, I have recollected whatever you have discussed so far. You know that force on the arm SP and this SP arm, where is that SP arm? This SP arm and QR arm, both are same value, IBB cos theta. These two forces are equal and they are opposite, right? See, look here. they are opposite direction, they are collinear, right? They are in straight line. So that what happened, the effect will get cancelled, right? So as when this cancels, what happens is, now you know that the this coil, it is not going to rotate about this axis, children. This is QR and this is SP. The coil is not going to rotate about this axis. Okay, it will not rotate this way. The coil will rotate only this way. In the magnetic field, the coil is going to rotate only this way and not this way, children. Keep it in mind. Okay, as PQ is coming up, simultaneously RS will be going down. Rotation of the coil is this way, not about this QR and SP axis. Make a clear point about that. So these effect gets cancel each other force. Okay, now if you see these force FPQ and FRS are magnitude are same, direction is opposite, that is it is upward and this is downward. They are not acting on straight line, so the two forces constitute a torque. As a result, what happened, the coil start to rotate in which direction? See, the coil is going to start to rotate in clockwise direction. Okay, children. Now we will calculate, this is the, to calculate torque, we are having the side view of this coil. Okay, now PQRS coil, you are going to view it sideways. So this end will be P, this will be Q, and this will be R, and this end will be S. Now you know that the breadth of the coil is B. Okay, so if I divide it into two parts, this will be B by 2 and this will be B by 2. So I will mark this end as A and the other end as A dash. Now to find the torque, you know the general formula, force into perpendicular distance. Force, you know, on the arm it is IAB, and the perpendicular distance you need, right? See, look at this point. On this arm PQ, the force is acting vertically upward, right? Now to consider the perpendicular distance of this force, you have to construct a triangle. Okay, from this point drop a perpendicular and extend this line, so you will get ABC, a triangle. If this is theta, from sin theta is BC by AC. BC is equal to, what is this BC? BC is the perpendicular distance. This is the perpendicular distance, children. This is perpendicular distance. If you want perpendicular distance BC, you will get B by 2 sin theta. So instead of BC, you can substitute B by 2 sin theta. So force on the arm PQ, torque on the arm PQ is equal to IAB B by 2 sin theta. Same way in this, for this arm, if you are going to calculate torque, this is the force direction, this will be the perpendicular distance. Okay, now same whatever you have done here, if you apply this same answer, you will get torque on this RS arm, it will be also IAB B by 2 sin theta. To find the total torque, you have to add these two, right? If you add these two and if you simplify, you will get this. Tau is equal to IAB sin theta. Children, this is length of the coil and this is the breadth of the coil. Length into breadth is area of the rectangle. Okay, small a, small b, you are replacing it as capital A. That is nothing but area of the rectangular coil. So torque tau is equal to IAB sin theta. So look at the diagram. How does the torque acts here? It is acting vertically upward. I have marked in cross. Net torque is acting perpendicularly upward. Okay, perpendicular to the paper at this point. If you want to represent with this coordinate, you can say that torque act along positive y direction. Now, how long this torque acts? How long this torque acts? See, imagine this to be the magnetic field, children. Initially, coil was in this position, right? This coil will rotate in this magnetic field. Coil will rotate in this magnetic field. How long? So that when this PQ part comes up, RS goes down, it will rotate, and when this part, which part? This A vector, when it comes parallel to this B vector, imagine this to be the magnetic field, B vector, okay? Till this becomes parallel, okay, A vector and B vector becomes parallel, this rotation of the coil takes place. That is what I have written. Torque rotates the loop so that the normal vector, that is n cap vector, otherwise a vector, align in the direction of B. This a vector should align in the direction of B vector. Now we will discuss the two more cases, children. Plane of the coil is parallel to magnetic field. See, look here, you take this green color as the magnetic field direction. Look here, how is the plane? You know which is the plane of the coil. This is the plane of the coil, right? Now you can see this plane of the coil is parallel to the magnetic field. Okay, this, don't consider this A vector, children. This I am talking about this plane. Plane is A of the coil is parallel to the magnetic field. What about this A vector and B vector, children? A vector is this, okay, this normal. This A vector and B vector are perpendicular, right? Theta is how much? 90 degree. If the plane of the coil is parallel, means theta will become 90 degree. By looking into parallel, don't write 0 degree. When plane of the coil is parallel to magnetic field, means A vector will become perpendicular to B vector. If you substitute 90 degree in this general formula, it will become 1. So torque is equal to NIAB. Torque will become maximum. In the other case, when the plane of the coil is perpendicular to the magnetic field, see, this is the magnetic field. Plane of the coil should be perpendicular. Now you can see this plane. Okay, this is the plane part, right? This is perpendicular. Plane is perpendicular to magnetic field, but this A vector and B vector are parallel. That is 0 degree. A vector, B vector is 0 degree. So plane of the coil is perpendicular to magnetic field, means A vector becomes parallel. So theta will become 0. So if you substitute 0 here, tau becomes 0. Okay, and finally, torque in terms of dipole moment, tau is equal to dipole moment into B vector, cross B vector. Dipole moment formula is I into A. I is the current in the loop and A is the area of this rectangular loop. So if you find the magnitude, you will get tau is equal to IAB sin theta. Got it, children? So you have to revise this answer. First understand this diagram clearly. Okay, before going into the application, understand the diagram clearly, children. Then go to the derivation part. Okay, hope you understood. Thank you.